Now let's take a look at individual weather systems and how we develop storms in the atmosphere. So when we're looking at winds in the atmosphere, the reason we have winds is because we have differences in pressure at the surface. Some areas have got higher pressure, lower pressure. If the pressure was the same everywhere, the air pressure, we would have no motion in the atmosphere. So winds are caused because some areas may be a little higher pressure, lower pressure, and we can cause this result in different pressures by heating the air, where the air may rise so that we'll have less air in a certain place so that it'll be a little lighter, or we can add water vapor to the air. There are different ways that you can change the pressure of the air, very small changes. But when we have differences in pressure, we get a force called the pressure gradient force. We can see here this line on the plot. And the force is always from high pressure to low pressure. That you can think of any physical object. If you have a cup sitting on your table, it won't move until there's a difference in force or pressure. If you push it from the one side, you're giving it higher pressure on the one side, and it will move in the direction from high pressure to low pressure. So the same in the atmosphere. When we have differences in horizontal pressure, then the air will start to move to try to balance things again, like we saw before with the radiation and the heat. So when we have differences in pressure, the air starts to move, and will always move from high pressure to low pressure. Now, over long distances, again, we said we have to take into account the rotation of the Earth, or Coriolis force. So what happens if the air starts to move from high to low, and we can see here in the bottom right, the high is at the bottom, low is in the top. The lines here represent the differences in pressure, or what we call isobars, equal pressure. So each line is like a contour map for height. This is a contour map for pressure. So we're going from high to low, and the pressure gradient force here is showing the force which wants to push the air, according to the blue arrow, from high pressure to low pressure. But as soon as the air starts to move from high to low, it starts to feel the rotation of the Earth. And in the northern hemisphere, again, this is an example in the northern hemisphere, the Coriolis force, shown here in green, will push the air to the right-hand side of the direction of the motion. And so the final direction of motion of the air is going to be the red arrow. And if we wait long enough, we'll see that the wind is going to turn. Instead of being directly from high to low pressure, it's going to turn, and it's going to be actually parallel to the isobars. It's going to be flowing between the isobars. So this Coriolis force, again, depends on distance, but also on the velocity. So the higher the difference in pressure between high and low, the stronger the force, and the stronger the winds get bent. And this wind, when it actually gets parallel to the isobars, and we can see then there's a balance between the blue arrow and the green arrow, between the pressure gradient force and Coriolis force, when they're balanced and they're opposite each other, we call this the geostrophic wind in the atmosphere. So the geostrophic wind actually flows parallel to the pressure lines, which is different to what I said in the beginning. Over short distances, we always get the wind going from high pressure directly to low pressure. So now if we have a region in the atmosphere where we have a center of low pressure, and everywhere around it the pressure is higher. So we can think of it like a bowl where we have the deep side, a deep part in the middle, and everywhere around the center of the bowl it's higher. So here in the atmosphere we have low pressure in the middle, and everywhere around it you can see these contours, we're going to higher pressure. So let's see what happens to the wind. So initially the wind will start flowing in the direction of the red arrow. It always goes from high pressure, which is on the outside of these circles. The highest pressure is on the outside, and it's going always to the direction of the center of the low pressure, where we have the lowest pressure. So the red arrow is what the force will initially push the air towards the center. But again, immediately, as it starts to move, it starts to feel the Coriolis force, which wants to move the winds to the right. And so slowly you start to see that the winds get diverted, and eventually we'll get the light blue arrows, which will give us the direction of the flow of the wind. And again, this is an example for the northern hemisphere. Eventually, if we have enough time and large enough distances, we'll get the winds which are flowing anti-clockwise around the center of the low pressure and not directly to the center of the low pressure cell. We also call this cyclonic flow because this is the same direction that the Earth is rotating if we look at the North Pole from above the North Pole. If we look at the Earth from the North Pole, it's also going in this direction anti-clockwise. So the winds around a storm which are going in the same direction as a rotation of the Earth, we call the cyclonic, and if it's the opposite direction, anticyclonic. So this is what we would get in the flow in the northern hemisphere, where the winds are going anti-clockwise around the center of the low pressure cell. And a low pressure cell means that the air is rising in the middle and causing the low pressure. And therefore, low pressure cells are areas on the planet where we have lots of clouds, lots of rain. These are stormy areas. And so when you have a big storm, you'll see that the flow is always anti-clockwise in the northern hemisphere. We could do the same example for the southern hemisphere, but Coriolis will be to the left. It'll be going in the opposite direction, and therefore, around a low pressure cell in the southern hemisphere, the flow will be clockwise in the opposite direction. And we can see this hurricane here, Hurricane Lotta, which you can see here according to this animation with the clouds moving. And you can very clearly see that this is rotating anti-clockwise around the center. The eye of the storm, the little hole in the middle, that's where we have the lowest pressure in the storm. That's the center of our low pressure storm. And the winds start to converge towards the middle because of the pressure gradient force, but because of Coriolis, they get bent and get diverted, and they're rotating around the center. So every storm, every low pressure cell, every hurricane in the northern hemisphere will always rotate anti-clockwise, and the opposite in the southern hemisphere. We can do the same for high pressure. So now let's turn the bowl upside down. So in the center we have the highest pressure, lowest pressure on the side, and now the pressure gradient is in the opposite direction. It's always pointing outwards. Again, initially the winds will go from high pressure towards the low pressure. So they follow the red arrows. Initially, the wind will be leaving the center of the high pressure and going outwards. But again, immediately it starts to feel Coriolis force. And so again, in the northern hemisphere, it gets diverted to the right-hand side of the motion. And eventually, if we have enough time, we get the light blue arrows where we see here around a high pressure cell, we have anticyclonic flow or clockwise flow around the center of the storm. So in the northern hemisphere, low pressure storms will always go anti-clockwise, high pressure will always go clockwise, and again the high pressure in the southern hemisphere will go the opposite direction because Coriolis is in the other direction, and it will be anti-clockwise. So if we look at a map of the isobars of the pressure, the dark blue lines are the pressure, the isobars where we have equal pressure at different locations. And we can see some areas will have center of low pressure. You can see the red areas here. Some will have a high local pressure in green. And just by what we've learned now about the geostrophic wind, we can say what direction the winds are blowing. So again, around the low pressure, we have anti-clockwise cyclonic flow around the center. So you can see the light blue arrows are showing the direction of flow. And around the high pressure cells, we have clockwise flow. And so you can see, we can draw in with the direction of the winds. And you can see that normally we have low pressure and high pressure together so that one kind of feeds into the other. If we go around the planet, you'll see low, high, they kind of alternate going around the planet. So based on the pressure maps we can get from different weather stations around the planet, we can know exactly what the direction of the wind is.